Okay, everybody, let us continue with our PowerPoint. Okay, so we have detecting radiation. How do we detect radiation? Oh, we use a Geiger counter. And this is what a Geiger counter looks like because you can't tell radiation because you don't feel it. It's invisible. It goes right through you. You don't realize it. Okay. Now, of course, you could also, all right, this is how Geiger counter works. They have different ones that look like this, more modern one. You could also use a badge. If you work in the hospital or X-ray technician, you might have a badge to see how much radiation you have. And one of the really cool things about, and I'll show you guys later, is this uranium glass that actually fluoresces, and it's very radioactive. And we'll see how radioactive it is with the Geiger counter, which is very cool. Okay, next slide. We have half-life. What is a half-life? Here I come up here now. What is a half-life? Half-life is the amount of time it takes for half of a sample to decay. What do you mean, Mr. G? Well, let's see. Let's start off with 10 grams of carbon-14. We have 10 grams of carbon-14. One half-life is when half of it decays. So is it an alpha? Is it a beta? I don't know, but it's decaying. So the half-life is one half-life, which is going to be, and it doesn't say on the bottom, you can't see it on the screen because my thing is in the way, 5,000 years. So in 5,000 years, half of it's gone. Where did it go? It transmuted. It went into a different element, it turned into something else. And then in another half-life, half of that, the 5 grams, is now gone. So now it's 2.5 grams. And then in another half-life, it's 1.5. So it's half, half, half. Mr. G, can I take a shortcut and just, no, you can't take a shortcut. Okay. And this is what the half-life curve looks like. It's actually very cool. Okay, next. So here we have, there we go. Bing, bing, bing. I'll move myself down. So once again, just as I said before, if you had 10 grams, it would take 5,730 years to be exact for it to decay half. So based on this curve, you can actually figure out how old something is by carbon dating. And this is how they do it. You start off with a certain amount of carbon-14, and after a certain amount of time, depending on where you are in this graph, you can tell how many years it is based on the number of half-lives. It's amazing. It's a great thing. Great for archaeology, finding out how old bones are. Very cool. Next. Okay, so here's some math practice. Don't want to spend too much time on this, but here it is. So we have iodine 131. Okay, so it's an isotope of iodine, and it has a half-life of 8 days. So if you start off with a sample of 80 grams, how many will there be left in 8 days? Well, let's see. Let's think about it for a second. So over here, one half-life is 8 days. So half would be 40. So there would be a 40 right over here. Then the next half-life is another 8 days. So that's going to be a total of 16 days. And then half of the 40 is now going to be 20. And then another half-life, half of the 20 is going to be 10. And another half-life, half of the 10 is going to be 5. So that's how it goes. Half, 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 half. Mr. G, can't I just multiply? No, you can't multiply. You have to do it. That's how you do it. And of course, here's some curves. Look at the curves of the different isotopes. They look the same. The curves are the same, but their half-lives are different. Look at that. This one, half-life is in hours. This one in half-life in years. And this one is half-life in billions of years. So different isotopes have different half-lives. Okay. So now let's talk about fission. What is fission? Fission is, and you'll see the nice definition later, I should put it in here. Fission is used in nuclear bombs and nuclear power plants. To fizz something, there's fission and fusion. Fission, like a fissure, is to cut open. So you're starting off with a heavy element and it's breaking into two smaller elements. Now, it's not the same as radioactive decay, it's fission. It's breaking into two smaller elements. But Mr. G, isn't that like alpha decay? It's breaking into, yeah, it's like that, but it's different because they're starting off with a really heavy element usually. So what elements are we usually using? Let's take a look. Uranium-235, very popular for fission. So what happens is you have uranium-235. It's okay, but in comes a slow-moving neutron. Neutron comes in, goes into the nucleus. It's slow enough that it just pops in there. Too fast, it'll fly through. So you need something to slow it down. We'll talk about that later. So it slows down and it goes into the nucleus. So now look at the atomic number. Atomic number is the same. It's still uranium, but now the mass has gone up by one because it has one more neutron. But now uranium-236 is unstable. It's very radioactive. So it can't handle it. It goes boom, and it breaks in half. Well, not half, but it breaks into two smaller atoms. Those two smaller atoms are krypton and barium. And when it does that, it's breaking up. It's giving off a lot of energy. And that energy, we're going to see how that energy is used later, comes out of the atom. And of course, it also gives off the very interesting 3 more neutrons. So if one goes in, 3 come out. That sounds very interesting. So here's another picture. If one goes in, 3 come out, then those 3, if they're able to slow down and hit 3 more uranium-235s, they're going to do it again. And then they're going to tell their friends, and they're going to tell their friends, and so on and so on. And it's going to go viral. It's a chain reaction. And if it goes continuously like that, uncontrolled, oh no, what happens? Boom! It's a nuclear bomb. But of course, we don't want that to happen. So what we do is, go back, is we're able to control it in a nuclear power plant. Hopefully, well, unlike the poor nuclear power plants that have blown up. But inside the nuclear power plant is here, and it's all protected. It's not that big compared to the little person, but there's a lot of shielding, a lot of cement protecting us from the nuclear stuff that's on the inside. Hopefully it doesn't blow up like okay, so hopefully it doesn't happen, but that's happening inside there, and the smoke that's coming out is not actually smoke, it's actually steam. It's just hot water coming out of there. So what that reaction is doing is giving off that energy. That energy is converted into heat, and that heat heats water. Steam turns the water into steam. Steam turns a turbine, and the turbine generates electricity. And there we have nuclear energy, which is a wonderful thing, and no CO2. And 40% of New Jersey's energy comes from nuclear. And France is almost 90 or 100%. So go France. Okay. Now, the opposite side of the coin. So we have atoms, big atoms breaking up. Fusion is smaller atoms coming together. Where does fusion happen? Well, you could make a fusion bomb. That's a hydrogen bomb. Different story. But the most common thing that you see all the time, every morning you wake up, it's the sun. And the sun is doing fusion. That's what is giving off all of that energy. And it's a lot of energy. Now, it's not really controlled, but it's far away, and it's okay. It's not happening near us. So that's good. So what's happening in the sun is you have 2 hydrogens. Now, these are isotopes of hydrogen because this is how we try to do it here on planet Earth. But in the sun, it's just taking regular hydrogen, and it's taking hydrogen, two hydrogens, put the hydrogens together to make helium. And it makes helium and energy, which of course is energy from the sun. So hydrogen is slowly on a sun scale, millions of years, billions of years, slowly coming together and making helium. At some point in time, it's going to run out of the fuel, run out of hydrogen, and then it's going to start taking the helium and combining them, making oxygen, and then combine those, and then make carbon, and then combine those to make silicon and make heavier and heavier and heavier elements by putting them together until it hits iron. And once it hits iron, that's the end, because the sun does not make any element bigger than iron. But Mr. G, there's elements a lot bigger on the periodic table than iron. What about all these buggers down here on the bottom of the periodic table? Well, our sun's not going to do it, but certain suns that are really, really big do that, and they do something called going supernova, where they go and it just smushes all the atoms together and makes all of the elements all over the periodic table, and probably a whole lot more that we don't know about. But then they decay from the other decay process, boom, 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 alpha, beta, gammas, and it decays down to the elements that we know. So let's compare, just for fun, the fission and fusion. So fission is where a big element is breaking up into smaller elements, and fusion is when two smaller elements fuse together to make a heavier element. And it would be really nice to be able to do that on planet Earth in a controlled way. I mean, we can do the fission. Nuclear power plants are great, but these little products are radioactive. So it's not that great. What are we going to do with the radioactive leftover stuff? It's not too good. You got to hide it somewhere. I don't know where you put it. Can't really throw it in the garbage. It's not good. So it would be really nice if we could take hydrogen and put it together to make helium. So then we end up with helium for balloons as a byproduct, which is really great because we get free, get lots of helium so we can blow up lots of balloons for parties. And there's lots of hydrogen because water is made out of two hydrogens. So you're able to take the water and make helium, and that would be like super awesome. But we're not there yet. Maybe in the future. So let's compare the two once again. So fission is where you have a heavy element and it's split into smaller. It can be controlled in nuclear reactors. If it's not controlled, the nuclear bomb. We don't want that. And then fusion happens in the sun, where hydrogen comes together to make helium, and they make bigger and bigger and bigger atoms. For now, we can't do that, but both of them generate a lot of energy, and energy is a wonderful thing.